All right, guys. This time we've got another question on the nozzles, and this is given as a part that is taking in gas. All right. Remember, I said we can have a condition whereby we are working with what? The steam. Or we can have a condition where we are working with what? With the gas. So there we are given on question number 2 of August 2023 exam, a gas of, at 860 kilopascal and 190 degrees Celsius expands at a rate of 4.5 kilograms per second through a convergent divergent nozzle. All right, so this is a convergent divergent nozzle that we have. As we know, guys, our sketch, this and that, that our convergent divergent is going to be like this. Just going to have our sketch. I explained this on the previous question paper. I think it was on the steam. Yeah, that one we had a steam. So just going to have something of this nature here. All right, so as we know that we have got the inlet conditions. All right, so this is our inlet. This is the critical part, which is we're talking about what? The throat in this case, whereby we've got the critical condition. Then we have got the exit or the outlet. All right, so this is our exit or the outlet. All right, you can just have this as the outlet. All right, so thus here at the inlet, you can just refer as 1, at the exit as 2, then at the throat as what? As a C for the critical conditions. So there we are given that the gas that is it at 860, meaning it is entering at 860 kilopascal. So that is the inlet pressure. So we have got the inlet pressure at 860 kilopascal, all right? 860 kilopascal, 190 degrees Celsius, which means the temperature also at the inlet. So this is T1. If we add 190 plus 273 to kelvins, that will be 463 kelvins. All right. Then also we have got the rate at which the gas is expanding. It is expanding at a rate of 4.5 kilograms per second. So this is referred to as the rate, which is given as 4.5 kilograms per watt per each second. Okay. What else? Through a convergent divergent nozzle to a pressure of, which is the outlet. So we are now at the outlet P2. That is the pressure there of what? 103 kilopascal. All right. And the gas has got the inlet velocity is what? Negligible. So remember, if the velocity is negligible, it means it is not considered. So the C1, it's 0 meters per second. We do not have that value. And also the gas constant and the adiabatic index are respectively. All right. So we've got the gas constant there, which is R. Remember, R represents what? The gas constant, which is 0.287. All right, that's 0.287, 0.287 kilojoules. Remember the gas constant. All right, that is kilojoules. Sorry for that. 7 kilojoules per watt per kg Kelvin. Okay. What else do we have? The adiabatic index. Remember, the adiabatic index is gamma there. This is the value of gamma, which is 1.4. All right. That's our adiabatic index. Since we are working with what? With air, which is the gas, we have to use this. That means this is an adiabatic process that is happening. Then the constant pressure heat capacity is, all right, the constant pressure. So we are given CP for pressure, constant pressure. Remember from our N5, CP there. Constant pressure, that's 1.05. 1.005, that's 0.005 kilojoules per watt per kg Kelvin, which is the constant pressure heat capacity. And so meaning to say, we do not have the constant what? The constant volume for CV. We are not given for the constant volume. It's not there. Just leave it like that. All right, then what else? That's the information that we have. That's the information that we have, only that. So I'm not saying you have to list down this information. It is just important that your information is presented properly. You won't struggle to answer these questions, all right? This is 20 marks. So just spend like a minute listing your information, then the rest of the minutes answering your questions. You won't have problems. All right. So we are given to calculate on 2.1 at the throat. So everything that we are going to calculate on 2.1 is what? At the throat. We are here at the throat here. That is where we are at the point what? At the point C. So like I said, for this topic, do not worry much because everything is given, the formulas. All you need is to understand how to apply and to use your formulas. All right. So this is what we are going to need on 2.1. So that's 2.1. So at the throat, we are asked to calculate the gas pressure. That is our gas pressure. We do not know. The absolute temperature. We also do not know the absolute temperature at the throat. The specific volume, we also do not know the specific volume at the throat. And also the velocity in meters per second, we do not know this. We are supposed to calculate all these. All right, so let us start with the pressure first. All right, so we're given to calculate what? The gas pressure, meaning to say the pressure at the what? At the throat, which is PC. So how do we calculate this? From your formula sheet, if you check, that will be the last page of your formula sheet on page number 5. We've got formulas that are listed about what? About this part of the nozzles, all these formulas that we have here can be applied on the nozzles. So if we check here, we've got the formula already given here for the what? For the pressure that we have at the what? At the throat. Guys, the formula is already presented. So we're just taking our formula as it is at the throat. All right. So the formula is stating that, all right. So this is our formula at the throat. PC is equal to P1 into 2 over gamma plus 1. This is everything into to the exponent of gamma over gamma minus 1. So that is the formula that we are having there. So meaning to say PC is equal to P1, the inlet pressure. Our inlet pressure, P1, is what? 860. So 860 into 2 over the value of gamma we are given as 1,4. So that's 1,4 plus 1 in to the exponent of gamma, which is 1,1 over gamma minus 1, which is 1,4 minus 1. So that is going to give you the pressure. So this is already given. All right. So if you simplify, we're going to get something like 454,322 kilopascals. All right. Since this pressure was in kilopascal, it means our answer is going to be also in what? Kilopascal. If you saw, also the formula for TC is also given there. All right, let's get back to our formula sheet. Here we also have the formula for TC at the throat. This is the formula for TC at the throat. TC is equal to T1 into 2 over gamma plus 1. So that is, we are just using or applying our formula as it is. All right, so we saw that here to find TC, the formula states as TC is equivalent to T1 into 2 over gamma plus 1. So that is what you're going to have in this case. We're just substituting our values. We have T1, the inlet temperature in kelvins, which is 463. We are given this. So this is 463 into 2 over gamma plus 1. Remember, our gamma is 1,4 plus 1. So this one was just a direct, which is 385,833 Kelvin. Okay. Then what about the volume? All right. What about the volume? Which volume are we talking about? This is not a steam where we used to calculate this V soup or whatever volume is V wet or V soup. We are talking about a gas. So the volume that you're talking about, just up here, they listed. All right, in this case, here. All right, we have got some of the formulas that we can use. All right, here is area. This one, it has got area, volume. All right, this one is not on this page. All right, it's not on this page, but there's this formula here that is given as, let me just write it here. All right, let me just write our formula, our formulas down. All right, we are on volume. Remember that from our formula, PV is equal to MRT, like this. But when you are taking this, when you're dealing with the nozzles, all right, it is taken at a condition where the mass is at 1 kilogram. So from this part that the mass is at 1 kilogram, it follows that you do not consider this because it's a 1. So from PV is equal to RT, you just divide by what? By P, because we want V. So this will be PC, VC, TC. So in order for us to have VC, it means VC is going to be R times TC over PC. All right, this is the formula that you're supposed to note, and also to note it even if you can know it that way. It's very, very important that you know it that way. So if you check, we've got everything in this case. So that is the volume. So VC is R in this case. Our R is given as what? The gas constant is 0.287, 0.287 times the temperature at the throat. Remember, at the throat, the temperature is given as what? Is given as 385,833. Everything over the pressure at the throat, we calculated the pressure at the throat, we got 454,322. So this one, it was just a matter of substituting direct. So this gives us the value of the volume at the throat, all right? So that was going to give us something like 0.243734, something like that. So it's going to be 244. The 7 is going to change the 3 into 4. That will be, so take note here, we are talking about the volume. All right. But if we consider our R here, this is our R is given as kilojoules per kg Kelvin. So the temperature here, it cancelled per Kelvin, per kilogram, the Kelvin cancelled. What about per kilogram? Where is it? Because here we are having kilojoules, take note, per kilogram Kelvin. So it means this volume is going to be in cubic meters per what? Per kilogram. All right, the joules and the joules, they cancel, but the kilogram remained. So it's going to be per kilogram, okay? So your volume will be the volume per kg. And also the other thing that you're going to need to know is that, remember we said our mass is given as what? As a kilogram. So we are taking it, since the mass is not included there, we are saying our mass is per each kilogram. For a certain mass that you be given, if they say the mass is 2 kilogram, then you multiply by what? By 2 kilogram. That is what it simply means. They per what? Per kilogram. Okay. So that is the other. That is how we could have calculated this. And we also need. We said VC. Why did I write the 2 VCs there? The other one is the velocity. It's CC. The velocity at the throat. Is that so? That was the velocity, not, yes, the volume and the velocity. So the velocity at the throat, it's CC, not VC. But this is what? C like this, the velocity like that. All right. So like I said, everything is there in your formula sheet. So this is it from our formula sheet. You're going to consider how do we take it. I talked about this when we had a question on, it was on heat. When you're dealing with the steam. All right. I said, if you check here, there are 2 formulas that we are considering here. All right. There are 2 formulas for CC for the speed at the throat. All right. There are 2 formulas there. There's this formula, or this one, and also this one. But which one is the one that we use? This one is when you deal with the steam. When you're dealing with the steam, you'll be having the enthalpy is H1 and HC. But when you're dealing with a gas, this is the one that you're going to use when you're dealing with what? With a gas. So you'll be dealing with the temperatures in this case. So this is the formula that you're going to take. And there's another formula again. Okay, let's write this one first. I'm going to show you another formula that we are going to use. All right, so from this formula, we saw that Cc is given as the speed at the throat is given as the square root of 2 times 10 to the exponent of 3 Cp like this into T1 minus Tc, all right, plus C1 squared. So that's the formula that we're given there. All right, so that is, we're going to have the square root of 2 times 10 to the exponent of 3 as it is. It's the Cp, remember, we are given this for the what? For the constant what? For the constant pressure. Cp for the constant pressure, that is heat capacity here, it's what? Cp 1,005. So that is the one that we're going to have there, 1,005. We have the value of what? Of Cp, the constant pressure, 1,005 times the change in temperature, T1 minus Tc. We have got the inlet temperature T1. Remember, we have got our T1 here as 463 Kelvin. So that's 463. All right, so this is 463 minus Tc. We calculated our Tc here. It was 385,833. All right, so this is what we have, plus the inlet velocity, and the inlet velocity, we are told that it's negligible, it's not considered. So that's a 0 there. There's nothing that you're going to have. All right, so if you had to calculate this properly from your calculator, you are going to get something like 393. That's 393,83 83457, something like that. So it's going to be 835 in meters per second. This is what? This is the speed. So the speed is measured in what? Meters per second. All right. There's also another formula that you can use to calculate this same speed at the throat. All right. So at the throat, we can use this formula, or we can have this formula at the throat. The speed is given as Cc is equal to the square root of 1,000 times gamma. So this is 1,000 times gamma times R times Tc, like that. So that's the formula that you're going to have to give us the speed at the throat. So that means we're going to have the square root of 1,000 times the adiabatic constant, which is our gamma. Remember, our gamma is 1,4. We used our gamma here, 1,4. Yeah, that is 1,4 times the gas constant, our gas constant R. We had the value of R here. Okay, here, 0,287. So that's 0,287 there. So you're going to multiply by 0,287. All right, times the temperature that we have at the throat. At the throat, remember our Tc at the throat is 385,833. So you're going to multiply by this 385,833, like that. All right, so this is the velocity that you're going to have at the throat, and that is 393,736 meters per second. All right, so if you check, it's just an approximate. We are using rounded off figures. It's not going to give us exactly these values that we have here. All right, it's not going to give us exactly these values, but as you can see, we are in the same range. All right, so that is how we could have calculated this value. We might need to use this speed. So if you use the second one, it's fine. But as for me, I'm going to consider this one. I'm going to work with this speed. For any other calculation that we need, I'm gonna consider that speed. All right, so this is what we had on the first part. It was, okay, as you can see, it was just direct formulas given. Then at the throat, they are now saying, calculate the area occupied by the gas in square centimeters. Take note, in what? In square centimeters, the area that is occupied at the throat. Also, the formula for this is given. It's there. They gave you everything, guys. So N6 is an advantage. Here, there is the area at the throat. The area at the throat is given by, we've got this formula here. So let us take that formula into consideration. All right, so this is what we're gonna have. Let me just remove this. That's 2.2. All right, so on 2.2, we are given that the area at the throat is given as that is this M here is the rate. The M that is this rate, not like the mass, is the rate. I'm going to explain this times VC over CC like this. All right, so that means this area is in square meters. All right, so remember, how do you convert from square meters to square centimeters? You multiply by 10 to the exponent of what? Of 4 to convert to square centimeters. So you're going to multiply by 10 to the exponent of 4. Your answer is going to be in square centimeters, okay? So this is the flow rate. This one is the rate of what? The rate of flow that you be given. So it will be in kilograms per second. So that is 4,5. All right, times the volume at the throat, VC. We calculated VC at the throat. Still remember we have that one here. That was VC here, 0,244. So this is 0,244. So this is what I want you to understand, is that this will be, remember, this was the mass per second. So it was kilogram per second like this. This is volume in cubic meters per kilogram. So the kilogram and the kilogram is already cancelled. So we are left with what? With the mass, with the volume and the time. So what is going to cancel with the time? What is going to cancel with the time? And this is the speed. That's why we put the speed here in meters per second. Remember our speed, like I said, I'm going to use the first one that we got here. So the speed in meters per second is 393,835, which is measured in meters per second. So what is going to happen is that, remember there, we are left with what? We are left with the cubic meters. So the meter was going to cancel with this cubic meter. Our answer is now in square meters per second, and this per second cancels. So meaning to say our answer is in square meters. That's why it's area. Take note. It's actually true even according to the area, to the units that we are given. But remember, I said we must multiply by what? By 10 to the exponent of 4 as a conversion to what? To square centimeters, because the area is needed in what? In square centimeters. So the area at the throat, if we are to do like this, we are going to obtain in square centimeters, we are going to have 27,8796 something like that. So it's going to be 880 to 3 decimal places. Like I said, on that part of conversion, you can even use the calculator to convert your units. To change to 3 decimal place or whatever number of digits that you want. So that was the idea of the question. We are at the what? At the throat. Okay. Then we move on to the other part of the question. Now we are at the exit, 2.3. At the exit, we are supposed to calculate the absolute temperature, the specific volume, and the velocity in meters per second. Now at the exit, and the exit is where we have what? 2. So we are at the exit. We are now working with 2 at the exit. So on your formulas, you must target where there is what? Where there is a 2. That's the exit. All right, so that's our question 2.3. So at the exit, remember, we want the absolute temperature there. We also want the volume. We also want the speed there at the what? At the exit. These are the 3 things that are needed: the absolute temperature, the specific volume, and the velocity in meters per second. So how do we calculate T2 at the what? At the exit. All right. Let us get back to our formula sheet. This time, okay, let me remove this one. Let me remove this one. All right. I just hope it is gonna make sense. I just hope it's gonna make sense. This time we are using normal conditions of calculating what? Of calculating the temperature. Take note about this one. This time we are using normal conditions. What am I trying to say when I'm saying we are now using normal conditions? Remember the one that we had, this formula here. Let me show you the formula that we had. That was here, this one. This formula is incomplete. It's an incomplete formula that we have. But in terms of at the throat, that is the formula for that. Even for the pressure, that is the formula. But this time we have to go back to the normal formulas of a gas. When we are dealing with a gas, remember, this is from your first page. From the first page, it is given as T2 over T1 is equal to P2. All right, that one, there's a one for volume and there's one for what? For pressure. So using pressure, it's P2 over P1 because we have got pressure there. To the exponent of n minus 1 over n. But this time, we are using gamma. So it's gamma minus 1 over gamma, remember, from our N5. All right, but if you check from the formula sheet, on the first page, but you have to use gamma because we are dealing with what? An adiabatic process. So meaning to say we can calculate T2 from there. T2 multiply here by T1 is going to be T1 into P2 over P1 to the exponent of gamma minus 1 over gamma, which is what? The pressure ratio. So this is the pressure ratio. So T2 was just going to be equal to T1. T1, we are given the inlet is 463. So like I said, this time we are using the normal gas laws, because it was the inlet, it is this pressure and this temperature, and it expands up to the exit where it is now at a pressure of 103. So it's now at a normal condition. But here at the throat, we have got its own condition about what? About the throat. So do not confuse what you have at the throat and what you have at the what? At the exit and inlet. All right, so T1 at the inlet, we say it is 463. We are given this into P2. We were given P2, 103. And also P1, we have this. So this is 103 over P1. We are given here 860. To the exponent of gamma, our gamma in this case is 1,4. So that's 1,4 minus 1 over 1,4. So this is going to give us the value of what? Of T2, which is 252,4929 and so on. So it's going to be 493 Kelvin. So that is our temperature there. All right, for the volume is the same, but this one we gonna have the same way as that one because like I said, this volume is going to be taken per kilogram of the mass. So we are still gonna have the same formula. V2 is gonna be equal to RT2 over P2. All right, from PV is equal to what? PV is equal to MRT, but the mass is taken at a kilogram. So that's why the volume will be cubic meters per what? Per kilogram of the mass. Okay, so be careful on that one. So V2 is gonna be R. In this case, our R is given as 0.287. So that's 0.287 times T2 in Kelvin, 252.493 over P2. Remember, P2 in this case was 103 there. So this is 103. So we're going to have V2. And that will be something like 0.7358 like that. So it's 0.704, which will be cubic meters per what? Per kilogram. All right, then the last one is the velocity at the exit. The velocity at the exit. All right, so as for the velocity of the exit, the advantage is that this one we are given from our formula. It's a direct formula. For the velocity at the exit, we've got C2 and C2 here. Which one are we talking about? This one where there are enthalpies is when we have got what? Steam. If you're dealing with steam. This one is when you're dealing with what? With a gas. So we're going to take this formula because we are dealing with what? With a gas in this case. Remember, this question is all about, or the condition there is on a gas. So we saw that on a gas, C2 is given as what? The square root of 2 times 10 to the exponent of 3 Cp, which is the constant pressure, heat capacity there, into T1 minus T2, all right, plus C1 squared, which is the inlet velocity, which you are given, that it's negligible, it's taken as a 0 there. So that is going to be the square root of 2 times 10 to the exponent of 3 times our CP, which is the constant pressure heat capacity of 1.005. So that's 1,005 into the difference T1. Remember T1, guys, is the T1 is 463 we are given there. That's 463 minus T2. We calculated our T2 there. That's 252,493. All right, so that is 8 plus C1 squared, which is 0 squared. All right, remember our C1, that's a 0 there. Unless if you are given, you use the value that you're given, but in this case, we are taken as what? Negligible. So that is going to give us the velocity in meters per second, and that will be 650.476 meters per second. That is the velocity at the exit. At the exit. Okay, so that is the idea there. That's the idea. Then the other part is now to sketch. This is just a sketch here. Sketch a labeled absolute pressure, all right, absolute temperature, sorry, entropy diagram. So it's a diagram that is from temperature and entropy, all right? Indicate at least one pressure value and one absolute temperature value, at least one, all right? No problem, let's see. So this is what you're gonna have. Remember what we are supposed to indicate is at least one temperature and at least one pressure. It's just a sketch. So the sketch of a temperature pressure is like, this is temperature entropy. All right, that's 2.4. It's temperature entropy diagram. Temperature entropy. All right, so for the temperature entropy diagram, we are going to have temperature in what? In kelvins. So this is your sketch. So here you have your temperature on this side. So this will be your temperature on this side. You're gonna have your temperature here in what? In kelvins, okay? Then on this side, this is your entropy, which is S. So it's just gonna have S for the entropy, which is kilojoules per kg Kelvin. Okay, so our diagram is going to be like this. All right, okay, why am I removing T2? I need T2. Let me just remove this part here. All right, so our diagram is going to be taken this way, just like what we had on that entropy diagram. All right, but this is just a sketch. So you're gonna have something of this nature. Okay. Okay. Something of this nature. So this is what is happening at the point 1. All right, let's say this is our point 1. Like I said, 1 will go straight to this point here. So this is a point 1, meaning to say at this point, we are going to have the temperature 1 that corresponds at point 1, and also the pressure there, which will be P1. All right, so P1 at the inlet, remember we were given at the inlet, P1 was 860. So it's enough to represent 1, but there can even indicate all of them. The mid one is the throat. It's PC. PC, we calculated this PC. Remember, we got something. It was 454. 454.322 kilopascal. And P2 at the exit, P2 is what? 103. This is 103 kilopascal. But they just said at least 1. You can indicate all of them. It's fine. Or just 1 or more. That is what it means. So here at this point, it corresponds with the what? The throat. So it means we are going to have the temperature at the throat here as it goes straight. This is the temperature at the throat. So like I said, this one is T1. Remember, T1 is given as what? 463. T1 here. T1 is 463. This is now temperature in Kelvin. So it's going to be T1 this side. All right, sorry for that. 463 in what? In Kelvin. This is our T1 here. Then this is TC, this one at the throat. Remember, TC was 385. Yeah, it was something like 385,833. All right. Then at this point here, we shall have, as it continues this time, this side, it will be your isotropic value. Then this one will be the actual value. For temperature, this one will be the actual value. So this will be your T2 somewhere there. So remember T2, we calculated our T2, this one, 252.493. So this will be 252.493 Kelvin. All right, so this is our T2. So that's the idea there. We do not have anything that is corresponding to the what? To the entropy. So just leave it like that. All right, so that is the sketch. So you need to know the sketch of each and every part of the diagram that is in your syllabus, depending with the information that you are given on that particular diagram, and also to insert one or two of the values that you're given. But if you check, you can answer as many questions as you can see from this information that we have. We shall see more questions from Meson African motifs till we meet again.